that you understand what went on in the lecture, we come back and support that with a topic quiz. And the topic quizzes are on Blackboard. And also it helps you to know that not only does it count toward your grade, but it also should identify weak spots that you have before we take tests, right? You understand? So when you look on Blackboard, and the problem is at the end of the semester, what I do is I turn those off because the grades are already set. And you can take them 2 times. We have people that would take it once, and then when they get their grade, they want to go out and take it again, and then they complain with me about their grades. So I turn them off at the end of every semester, and then this time I forgot to make them visible. But it is in the syllabus about the topic quizzes. Oops. So this should be in course content, and then there should be a section under topic quizzes. And this is what was invisible. And then these are the top. And of course, what are we working in now? We're working in copper, right? So right now, we should have basic electricity 1 and 2 due in chapter 1. We're going to deal with soldering a little bit before I go to our next lab. And right now we're working in chapter 2 of our lectures. You'll need to go out and get those done as soon as you can. When's our first test? Coming up pretty soon. Next week, right? Should be the 5th class. So we're in the 4th class right now, so we need to look and see about see what date it's actually scheduled on. Yeah, the first test we hold off to the 5th class, and then after that we have one every 4 classes. If my calendar comes up, looks like Blackboard's locked up on me. If y'all can go look at the calendar and see exactly when the first test, it should be already on the course calendar. There we go. And holidays, so here's our first test next Wednesday. Of course, Monday's a holiday, right? So the test is the next class. So I'll post the review today. I'll try to get up there today for the test. To help you study for that test, that's what those topic quizzes are in there for, is to identify. So the topic quizzes don't count near as much as the test, right? You understand that? And what the topic quizzes are in there for is to help you identify what's going to be on the test, for one thing, and also helps you identify what you don't know. Of course, you can take the topic quizzes twice. After that, you're memorizing answers. You're not really knowing what the topic quiz does. So the same questions every time. We could pull from a pool, but I don't do it that way. So you can take them twice and get the best grade that you want. It keeps your highest grade. So what that means, if you take it the second time and you score lower, it's going to keep your first attempt.
Is it 6 quizzes?
So
6 quizzes.
No. There's electricity 1 and 2. That was probably the longest lecture we've had so far. And that's where we just went over Ohm's law and series and parallel and all that. Even though most of y'all already know that, so that should be a pretty easy quiz. But the only requirements for this course is the EET 100. And so that means sometimes we get people in here that hadn't had DC, and they don't know series, they don't know parallel, they don't know shorts, they don't know opens and that kind of stuff yet. And there's some AC knowledge required in this course. Some students get in here that's even had DC, but they hadn't had AC yet. So what we do is we teach that basic knowledge. And then chapter 1 we're through with, and that was a pretty short chapter. Chapter 2 is a pretty long chapter. It's got a lot of information in it, and we should finish that up today. And then we'll look at soldering, and we'll look at terminals and stuff like that. I think the next lab we actually start terminating cables and splicing cables, not cables, conductors. And of course, one main way that we actually splice conductors is solder, because that's probably the most physically strong, electrically strong connection that we can make. So y'all got all weekend. So go out there and do those 3 topic quizzes, and we'll see how far we get today. We'll have to see what's on the quiz. I'll take a look at the review and see if y'all need to do that next one too before the test. And that was my fault, because I didn't make them visible, because I made them invisible after I taught the class last time. But we're working inside of what we'll call chapter 2. I mean, it's good enough to leave them in chapters, because that's basically what we're doing, even though you don't have the book. But we make the PowerPoints really, really detailed. In fact, they're probably better than the book anyway, because I've never had a book that teaches everything that we probably need to do in the course. I've only had one that did that. That was one that I wrote. So we took through, talked about cables, a little bit about fiber optics, but we're not going to do very much on fiber optics, because it was covered in this book, and I might go out and actually take all this out, since we're not using the textbook anymore, and that way we can totally split the course between fiber and metal. And we looked at this, this was basically a review from the first part, the best conductors of electricity and that kind of stuff, what determines what the resistance of a wire. Or a metal conductor, or we call them wire. We looked at the American wire gauge. We looked at that formula just to let you know there is a formula that determines wire numbers. It was very strange when I first got into the field. Normally when things get bigger, what they represent get bigger, but that's false in the American wire gauge. In the American wire gauge, the bigger the gauge number, the smaller the wire, right? We talked about circular mills. It's very popular to rate. Anything above 4/0 is going to be surely rated in circular mills. There's one thing that I just added to the PowerPoint this morning, just a little different, and that was this right here. And I noticed this. The problem we have with stranded conductors is that as soon as we take the insulation off the conductor, it has a tendency to do what we call bird caging, which means it tries to do what? Spread out. So I don't know if y'all noticed that, but when you do that lab on that micrometer, you need to wrap those stranded wires up and twist them really, really tight. Or if you don't, you're not going to get the right gauge, because as soon as that micrometer hits that side, it's going to push those things and make it try to spread out. So the way they actually do the circular mills for a stranded cable is they take the diameter of one conductor squared, and then they multiply it by the number of conductors, and that's the way they set the gauge. So if we wanted to accurately do this, what we would do is we'd have to count the number of conductors in the strands, right? Take the diameter of one of them and then multiply it by that number. And that's the way they actually come up with the actual gauge of that. Of course, they know that when they wrap the strands. I'll see if I got a video. It's really, really neat, the way they make stranded cable, and also the way they put the insulation on the cables or the conductors also. And we went through all this, but I just wanted to make sure we came back and touched on that, because I just saw that in one of the handouts, by the way, that's up on the. So this is where we're at right here, the ampacity. This is the amount of current a conductor can carry without exceeding an allowable operating temperature. And of course, they add a bunch of stuff here. They say, okay, it's some of the stuff we talked about is the material, the size, what type of insulation you put on it. Of course, the ambient temperature, how you install it. A lot of people don't understand that. We're getting a problem with a lot of communication cables is people don't know how to install those things. Then they wonder why their network don't run at the speed it's supposed to run at, right? Insulation methods, number of conductors in close proximity. Now, and this is in conduit. If you pull, y'all know what a conduit is? Everybody okay with a conduit? What is a conduit? It's basically a tube or a rectangle that we put wire in. And what's the purpose of the conduit? Protect the cables, wires. That's the main function of it. But once you start running a lot of conductors inside a conduit and each one of them's getting warm, then that heat is going to be built up inside the conduit. So when you look at pulling cables, they specify the number of conductors you can actually pull through that conduit. You never, ever, ever, ever fill a conduit up. Well, I'm sorry. You're not supposed to ever fill a conduit up. Saying not to ever do it, That's like saying you never, ever, 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 ever run a red light. How many people run a red light in their life? You're not supposed to run them. So people do a lot of things they're not supposed to. And then over time, a thing starts happening, and then all of a sudden the system doesn't do what it's supposed to do. And then you call, hundreds of thousands of dollars to come up and undo something that wasn't done right in the first place. And then the actual current levels. What I gave you is, we have what we call an ampacity chart, but the problem with our ampacity chart is that it's rated at 20 degrees centigrade in free air. So that one on, how many conductors do you know that's operating at 20 degrees centigrade in free air? None, right? Y'all understand? But we do have a lot operating in free air. A lot of our power company conductors are free air. They don't put jackets on, okay? Or they don't put insulators on. So NEC came up with a chart. It used to be 310.15, but in the new code, 16. But for some reason, they like to do that. In the new code book, it's now 310.15, and that's the handout that I gave you. And this is also available up on the Blackboard site in course content in reference material. So we looked at the ampacity chart, reference material. We look at the ampacity chart. By the way, y'all have access to this Blackboard all the time, right? You understand? So even when you graduate, if you need this stuff, you can do what? You can still log in, as far as I know, and get access to these. And there's a lot of good information right here. So this is NEC code table, where's it at? 10.15, which is multiple cables, by the way. They got a B and an A and that kind of stuff. And if you got an old code book, you would look this up in 310.16. But they did some stuff to the new code book that more aligns to what we do. So this is the chart I just gave you out, and this is our ampacity chart. You notice this is 310B to A. This is formerly this, so there's a lot of 310 tables that go with trying to figure the ampacity of a conductor. Now, if we look at the first ampacity chart that we looked at, it says a 14 gauge wire is rated at about 32 amps. And in the 310.16 table, they had it rated at 20 amps, which was very confusing because you always and what does the overcurrent protection device do? It protects a conductor. That's what it protects. It's not in there to protect the load. It's in there to protect the conductor. So normally what you do is you fuse the wire at you fuse it or put a breaker in there for the ampacity of the conductor. The problem is we know that a lot of things affect the ampacity of a conductor. So we call this die rating. How do you reduce it down depending on what environment it's going to run through, how many conductors you're going to pull together, which would be this table right here, right? You understand? This is the ampacity chart that's in the National Electrical Code uses. Now, what changes? Well, what changes the ampacity is what type of insulator you put around there. So if you got a certain type of insulator that is allowed to run hotter, then of course you can get more ampacity, right? You understand. Of course, those insulators will probably cost more money. Does that make sense? Yes or no? So standard house wiring, we run it in what we call a thermoplastic. And we'll look at these different designators here. So all these across the top are designators for insulator types. And also jackets too, we'll look at before long. And they rate it at 60 degrees centigrade, 75 degrees centigrade, and 90 degrees centigrade. Okay. And you can see as the heat rating of the insulator goes up, it allows us to conduct more current in the wire. Does that make sense? Okay. So we start off, if we use a TW insulator or a jacket, then we'll fuse it. Our overcurrent protection device would be rated at what? Didn't y'all get one? We're rated at what? 15 amps. If we get it in any of these type of ratings right here, then we could rate it at 20 amps. If we come over here and use any of these type of insulator jackets right here, then we could actually run what? 25 amps through that. Now notice all of these are below the 32 amp rating of a 14 gauge wire in what? In 20 degrees centigrade in free air. And this is what electricians use to decide what service they're trying to run, what conductor they're trying to use. And of course, now over here, this is the way we dirate it if we run it at a certain, so over here it says if I run it between 123 degrees, if I run it at between 123 degrees Fahrenheit and 131 degrees Fahrenheit, then I would take that ampacity, and I'm running an insulator that's rated at 90 degrees centigrade. I would take that ampacity and multiply it by 0.76. And then that's what we would fuse it for. So even NEC says, okay, this is for average situations. And odds are these are going to be the temperature ranges you're going to run these conductors. These are what you're going to use, right? You understand. And then, of course, now what we can do, if we don't run it in that environment, if we run it through a boiler room or something like that that's extremely hot, then we can direct the cable and see what we can actually fuse it at, right? Does that make sense? So national, over here, this TW cable, this is standard cable that we use in house wiring. A lot of people call this Romax right here, because Romax was the original company that, and this is TW cable right here. Now this is a cable. So what's the difference between a cable and a conductor? So y'all should know that now. And sometimes they're used, the terms are used incorrectly. Sometimes they call conductors cables. But some of them are legally called that. It's just that your other conductors are hard to see. So this is called Romax, as soon as it comes up. So this would be the TW right here. Okay. Now this is the jacket, and these are the conductors. And these conductors actually have a true jacket on. So this is 14 gauge wire. So this right here would be rated for a 15 amp service. And a 20 gauge wire would be rated for what on your table? I'm sorry, 12 gauge wire. A 12 gauge wire would be rated at what? Tw 20 amps. And of course, if you're going to rate the cable at a different amperage, then you don't want devices that run that's capable of running. You don't want to put 20 amp devices in a 15 amp service. So what they do is NEMA, which is the National Manufacturers Electrical Association, National Electrical Manufacturers Association, has set up different standard plugs that y'all use. I can't put my camera over there, but there's a 20 amp plug on the wall right there. Can you see something different about it? And we'll put the NEMA. Yeah, well, it's got the little L shape or the T shape coming out one side. So if you bought a 20 amp device, it would have a plug that uses that little thing in there. So that means I couldn't plug it into a 15 amp receptacle, right? And now I can plug a 15 amp device into this thing because it's rated at 20, but I shouldn't be able to take a device that needs 20 amps and plug it into a 15 amp receptacle. So I don't know if I put the NEMA things up there or not, but I'll do that. That shows you all the receptacles and all of the plugs and everything, what their currents are rated for, and all different types of things too. So 240 would have a different plug like that. Even though I could legally wire that plug over there for 240, it would never pass code, right? You understand, because it's a different plug. So you got to use certain plugs for certain receptacles, different things. So here's the Romex. You're down at their end. And this is TW. And we'll look at what those different designators stand for. So what's nice about that cable is it has both a jacket and then it's got insulation. So the function of the jacket, of course, is to isolate the electrical conductor from other conductors and also to isolate it from you. So that means we can handle a lot of conductors even when they're electrically hot and not worry about it as long as our insulation is okay. That makes sense? Now the function of the jacket is to provide additional thermal, chemical, mechanical, environmental protection. So basically a jacket, also called a sleeve, a jacket is there to protect the cable from the environment. An insulator primarily is in there to keep that voltage in. Keep all that push inside that conductor, right? You understand? And not have it go places it's not supposed to go. Now, a lot of times a conductor's insulator and jacket are exactly the same. But if you've got a cable, odds are, if you've got a cable, then what is a cable? The true definition of a cable. Multiple conductors that share a common jacket. That's the definition of a cable. Two or more, actually. Two or more conductors that share a common jacket is what a cable is. But a lot of times we call like fiber optic cable, we call it cable, so it's a misnomer. But it has several components, but it only has one conductor. So, like I said, so a lot of times the industry picks up terms that are not actually what they're defined at, right? You run into that all the time. So insulation is classified as chemical resistant, heat resistance, moisture resistance, or oil resistant. And we can pick that up from those some of those designators. So if you look at your insulators, if you see an H out there, that's 75. If you don't see an H in the next few letters, that indicates that's 75 degree. If you see two H's, it means it's 90 degrees. You'll see that. So THH will be rated at 90 degrees. That makes sense? Then if it's got a W out there, what do you think that means? It can run in moist environment. So THHW would be thermoplastic, rated at 90 degrees, can run in moist environment, which is pretty neat. So these are different types. We can have rubber, we can have elastomers, we can have thermoplastics, thermosetting, nylon, Teflon, mineral insulation, paper, So you can see inside that that cable that it has paper insulation in there for the ground wire. So the ground wire itself does not have insulation on it, but they run paper in there to insulate the ground. Solid, gas filled, oil filled, varnish, and ceramic. And we see this a lot, especially in magnetic cable. So the insulate. Oh, where's my magnet? Oh, yeah. So this is that cable. Yeah. So this is, we call it varnish. That's just painted on there basically, right? And this is what we call magnetic cable. Varnish, cambric, polypropylene, silicon, Tefazol, I think, and Alzar. These are different type of insulation we could have. Are we okay? The jackets and shields. So we have shields. The jackets can be, and unfortunately, we're in the wrong lab. I need to go over to building A, and I'll bring some of these over here next class. A lot of our cable spots and stuff is actually over in building A because we had a lot more room to store it over there, and plus that's where we used to teach the class all the time. Here lately it's turned in that we teach it more over here than we do over there. So some of our demonstrations we'll have to show you. We could look this up though. So we have a polyvinyl chlorine, which they call PVC, polyethylene, polyurethane, thermoplastic, elastomers, which is the same as some of your insulators, Flamarest. What do you think this stuff is? It would be flame retardant, right? Metal clad. This is where we actually get into some true cables. These are a lot of times, and these ceilings are too high, so we can't see some of this metal clad cable. Normally, when we run conduit is rigid, right? Y'all understand what that means? Yeah, it don't want to flex. So if you see this conduit running across the ceiling here, see those metal pipes running, that's conduit. But the problem is that when we get into suspended ceiling, the suspended ceiling is constantly moving. Okay. And those lights just basically sit on on rails up there, so they're constantly doing what? Moving. I might need to run a motor. Well, a motor constantly vibrates, right? You understand? So I go out to my air conditioner at my house, and when they make the connection between the box over to the air conditioner, it uses metal-clad conductors. This is not conduit. It means the jacket is actually what? So let's bring up this, and we'll see if we can bring up some pictures. So we'll just look at metal-clad cables. Let's see. Come on, catch up with me. Yeah, metal clad. And then we'll look at cables. So these are metal clad cables. So the cables themselves, this is a pretty good picture. So the outside jacket of the cable is actually made out of what? It's made out of metal. It's usually ribbed, so it makes it what? Flexible. And normally we run these from so if I was to look up inside this plenum up here, which is the space between the artificial ceiling and the real ceiling, we would see we'd have boxes up there, and then running from it would have conduit running all the wiring, dropping down to the actual light fixtures would be this metal clad cables. So that way it gives the watt, it gives the suspended ceiling the ability to your air conditioning system. If you got an outside air conditioning system, they probably run metal clad cable from your disconnect over there, because your whole air conditioner just constantly does what? Constantly vibrates. So if you see MC designators, what is it? MC? M stands for MC. Yeah, metal cable or metal clad would probably be more correct. I can't remember what the ALS is. I'll have to go back and look at that and see what that is. But frame retardant, so we have cables that have jackets on. But what's the function of the jacket? The main function of the jacket is to protect it against what? The environment. The main function of the insulator is to keep that pushing. So it's in there to protect the conductors from each other and also to protect you from that conductor, right? That makes sense? So this is a typical low voltage cable, but sometimes what? The jacket is the insulator. Does that make sense? Now if you look, where's that Romex at? So this guy is pretty neat in that it actually has a jacket. Because a lot of times when we get inside our box, what we do is, so we run it through our walls. You don't need to separate this while it's running through your walls. This protects us. We can use cable clamps. They come this size right here, where you drive them in, cable nails where you can drive them in and hold it and support it. But once we come inside the box, the pull boxes or the boxes, then we strip this jacket off. Here's the paper insulator. You'll see that in there for the wall, for the ground conductor. And then around this, if you look at the black wire where it's actually, you can actually see the nylon jacket. Can y'all see it? Like, and unfortunately, when I bring my camera up, I'll lose my ability to pause. I'll lose my pause thing for, there it is. So I look at the conductors, and I turn my camera off, okay? So this is, these are conductors coming out of this little DC motor as soon as it comes up. Come. Right here. And of course these, the insulator and the jacket are the same. So here the insulator is actually what's protected. Not only is it keeping the voltage inside the cable, inside the conductor, it's also what? It's also protecting us against the environment that little thing was designed to run in, which is not very. These guys right here. This is a cable, by the way. So here's the jacket, and then here's the two conductors. And somehow I stopped my PowerPoint. So this is the basic makeup of a low voltage cable. But sometimes they don't have the what? They don't have the jacket. The jacket and the insulator are together. They're not separated. But on the Romex cable, you can actually see it what? You can see the insulator and the jacket. This is a medium voltage conductor. Now the problem is, I don't know if the next slide, yeah, this is what we have problem. The higher the voltage. Now these things generate magnetic fields. And magnetic fields tries to concentrate into metal. And of course we have a lot of these cables running pretty close to metal. So what would happen, or even other conductors, If we didn't do something, then all the stress, so if I laid this cable close to some metal, then it would try to concentrate all your stress on one side of the cable. Now, what would happen is if the thing is rated at 600 volts, if the insulator is rated at 600 volts, that's 600 volts all the way around. If I try to come, which would be distributed, if it should be distributed equally around the insulation. Does that make sense? If I come over and stress that thing and move all that electrical stress to one side of the cable because we run it close to another chunk of metal, then we're gonna go arc through the insulator. So what they do on these medium voltages and high voltage cables is they surround the conductor with what? A semiconductor layer. So what happens now is that the current is the semiconductor layer. A semiconductor is neither an insulator or a conductor. But what that does, it helps distribute the stress around the entire insulator. So when you get into some of these high voltage or medium voltage cables, a high voltage cable will have multiple layers. So this says conductor, then it has a what? Semiconductor layer, then it has a what? Insulator, then it has a what? Another semiconductor label, and then odds are it's going to have a metallic shield. So they put the metallic shield around it. It's put around there evenly to do what? To equalize the stress on those insulators. So this is a high voltage cable that's been spliced. And of course, it follows this technique right here. In fact, this would be considered a medium voltage cable. So this is a medium voltage cable. Looks like it's about a little over ½ inch, so I don't know what the circle mills on this would be. You can't see the jacket because it's been spliced. And what you see here, this is the shield. It's nothing but copper wrapped around. This is the semiconductor layer. So when you pass this around, this is heavy. You see this black layer right here, right up against the conductor. There's the semiconductor layer. Here's the insulator. Here's the second semiconductor layer. Here is the what? Shield. We can't really see this is the outside jacket. This is another layer, this mesh right here. I don't know if this is semiconductor or not, outside the shield. So splicing these things, it takes a lot of, to splice high voltage cables or to terminate high voltage cables, you got to come back and reproduce all these layers. That makes sense? Because if I didn't reproduce all those layers, so you buy splicing kits for these cables, and they have all the layers in there, and you put them on one at a time. It's just really harder to do. We got some videos on splicing high voltage cables. So it took a lot of work for these guys to come in here and just terminate this. So this is one form of termination. Okay. This is actually a stranded cable, but you won't be able to bend it. But we could still roll this up on a spool, right? You understand? So the bigger the cables, but if this was solid, they couldn't even roll that up on the spool, right? You understand? So this is a medium voltage cable. I can't remember exactly what it's rated at. We don't have any markings on the cable, but you can actually literally see these different layers. So splice kits for those cost about $300 or $400. So we don't splice them, but we do look at videos on how to splice them. So y'all not going to be able to splice high voltage cable. But there's plenty of videos out there. I didn't want to close that. It shows you how to do that. And so what are all these different layers in there for? The shield, the semiconductor layers. Here's the actual conductor. But what do we put all these layers in this cable for? To do what? Equalize the stress. So that means the stress doesn't try to shift to one side of the cable because I run it next to another cable, or because I put it against a piece of metal. Y'all know magnetic fields concentrate through metals. So what would happen if we got this so close to a metal, like when they run it on that tower up there, you know, the supports up there are metal. Well, what would happen is those big old high magnetic fields would try to stress toward the top, right? You understand? And they don't let it do it. They just run this cable. And these guys are very expensive. Distributing the electrical stress. That's what all those layers are in there for. This is coaxial cable. We already showed y'all this. This is what we use in communication. We very seldom use this to transmit power, but we do use it to send information. So we got two things we're using these electrical conductors for. We're using them to send power, or we're using them to send information. So the coax cable that comes into the back of your TV is not in there for power. It's in there for information. That's where all your channels come through. And you still plug your TV into the wall, right? So those conductors that runs from your power outlet into your TV, those are power conductors or power cables. Those are actual cables. And then coming in from the back of your TV that uses that little FNC plug back there, the twist plug, those are for information. Now, this is what they call it, and this is one of the terms that that is misleading. Normally a shield, we only ground a true shield. We ground it on one end. Because if you ground it on both ends, you turn a shield into a conductor. So what we want a shield to act like is we want a shield to act like an antenna. So if you went out there and took a ground clip and put it on top of your radio antenna and ran it down and put it on your chassis, your radio wouldn't pick up anything. Right? You understand? Of course, most antennas now are coated in rubber. It'd be hard to do. But on a coax cable, this is a conductor. So it's grounded it's on common on both ends. So the name is different, but we have no option but to use what the industry calls it, right? You understand? So here's our two conductors. We have a center conductor, which can either be stranded or solid. Then we have an insulating layer, and then we have a shield, which is the second conductor. And then we have a jacket. I think I showed y'all these. I don't know if I got one strip. And I didn't bring it. And you have to strip this thing. For one thing, the spacing between this conductor and that conductor has to be precise. Because what this does is this sets up a capacitor. So here's a conductor, here's an insulator, here's a conductor. It sets up a capacitor. And what determines the capacitance is the length, the size of the plates, and then of course what you use to separate the plates determines what we call the capacitance. So if you screw around with this, then you screw around with what we call the impedance of the cable, and we'll talk about that later. I don't know if you can see the layers. We can't strip that with this. We have a special coax stripper that I'll show y'all, which is it's really, really good. Okay, y'all go ahead and take a break, and I'll go pull one out. So coaxial cable. Coaxial cable is given what we call an RG number. So if you ever see like an RG58, RG59, or stuff like that, that means that's definitely a coax cable. RG stands for Radio Government, but it's kind of a cable that was originally developed of course, by the military to use to send information on. And it's also rated at a frequency. This guys are able to handle extremely high frequency. RG59, these are the two that I've really ran into. It's RG6, RG59, and RG58. I think we've got RG58. Trying to find a piece of it. It's got the jacket on there. Yeah, so this is RG58. RG58 is a 50 ohm cable. And this might look familiar. This is the cable that that the cable company uses. And you got to be really careful when you. So we use the term strip. What does strip mean? So strip, what does that mean? Not strip tease. When we do something with a conductor, what does that mean? Take off the insulation in the jacket. The problem with cables, and of course we want to do this without nicking any wire. We call it scribing. You know, we have scribes that we use we call them glass cutters. And so you can't go out there and cut a knife, but you can take a dang glass cutter and put a little scribe mark down that thing, and that sucker will do what? Break perfectly. Well, we have that same problem with metals, scribing metals, and that means putting little nicks in them. Well, once you put little nicks in a solid, it makes it real easy to do what? Break at that scribe mark. So we have special strippers. This is a coax cable stripper, which is pretty neat. And you literally adjust it, so it takes a little while to adjust it, but it's got two blades in it. It comes with an Allen wrench. And then these are the two set screws that you use to adjust the depth of the blades that do the stripping. And once you get it set, you can just move this around for RG8 or RG59 or RG6, and it will strip all those cables at the same setting. We have it set for RG8. I don't know if y'all can see the stripping blades, but I'll pass this around. And what we do is just lay the cable out till it lines up with the end, take our finger, put it in the hole, spin it around, and then pull it apart. And if it's right, we should see, if we got it stripped right, we should see basically no conductors. So here's the shield. This uses a copper shield, and different cables use. RG6 uses a aluminum foil shield, and you'll see a lot of them. If you took the one your cable company had, it's going to use an aluminum foil shield, but then they have wire that wraps around it so you can make connection with the shield. This uses a stranded conductor. Looks like we need to adjust it a little bit, but anyways. And on the cable, you should see RG8/U coaxial cable. So this is true. So on that, you just can't, when you splice it, can't just cut the wires, strip them off, and twist them together. Because as soon as you do that, you mess up that spacing between that inside conductor and the outside shield. So it takes a little technique to learn how to splice that. You have a special splice that will try to show you all that we use to actually splice the cable. So these are communication cables. They can handle frequencies anywhere from 0, so DC, all the way up into the gigahertz. Very reliably. These are different variations of coax cable. We have multi-conductor coax. I've never seen the twin axial cable or the multi-layer cables. I haven't seen these. These are basically the cables that I've dealt with. When originally we came out with networking computers, we networked the computers with coax cable. So there's literally miles of coax cable running up in the plenum of this college from where we first set up our college network. Of course, that's before they came out or figured out something called a differential interface that allowed us to use twisted, what we call twisted pair cable, which is this card. And I think this is probably covered here. So a lot of our cables, our communication cables, we'll use what we call twisted pair. And of course, got to be real careful. And the problem is, a lot of people try to strip these with a pocket knife, and they'll put that thing across here, and instead of scribing it, they try to strip it. Now, if you use a pocket knife, what you need to do is you need to scribe the jacket, right? You understand? And then when you scribe it, take it and bend it and break it. Don't cut through the jacket and actually hit one of your conductors. We have these cable strippers right here, which are pretty neat. All you do, same thing, lay it in there, and then you spin it around, and then it should strip the jacket. And this was not adjusted right. So this is what we call twisted pair cable. And you'll see why it's called that. Because the conductors run in groups of twos, and they're twisted together. And then it's got a nylon cord that runs in here that adds physical strength to the cable, so we can pull the cable. Pulling the cable is a technique of getting cable through conduit. So what we do is we run the conduit, and we run what we call a cable puller through it, which is kind of like a wire. And then we connect it onto the cable and pull it back through the conduit. Well, the problem is, if you put a lot of stress on a very small conductor, it's going to elongate on you, right? You understand? And that's going to change the gauge. So a lot of these cables that has this real small conductors will have either nylon or something in there that allows us to pull it without putting stress on the wire. That makes sense? So that's what that's there. And this is twisted pair, which is probably going to come up here pretty soon. This is communication cables. This is literally wiped out coax cable. Twisted pair cable has wiped out coax cable in network. So now we either network through RF, through what people call Wi-Fi, or we network through twisted pair cables. So when you look up at this switch up here at the top, those are all twisted pair cables that, just like you're holding in your hand. So when you splice that, you got to be very liberal. You get how far you untwist those things, because if you untwist those, you change the characteristics of the cable. And you see people that don't know those. This is dB. dB is a technique we use to represent losses and gains. Have y'all heard of dB 4 decibels? I hope so, but most people don't understand what it means. It's kind of like engineering notation. Engineering notation, we use milli and micro, and what it does is it allows us to represent very large or very small numbers with very few digits. And this uses power of tens. We'll look later on. So every calculator's got 10 raised to some power, and that's all that dB deals with. And we have a lecture on that before long. But dB, the bigger the dB loss, so 3.6 would be more of a loss. So 11.2 dB would be more of a loss than 3.6. So what they're saying is that at 100 megahertz, RG59, we'd only have a 3.6 dB loss over 100 meters. If we ran it at 100 megahertz, then it would actually have 11.2 dB loss. And we'll show you how to do that. 3 dB is pretty much, the limit on most communications, so this would be probably unacceptable, but it would still work. And like I said, we got a whole lecture on dB. What you're looking at there, that's what we call a Cat 5 cable, Category 5. So a stranded cable, networking cable, is given a different category. So Cat 3, which is what we first started running at, Cat 4, and now we're running on Cat 6, which is not listed. Cat 5 works real good at the high speeds, but we do things that we normally won't do. This is twisted pair. And you can actually see that on that cable. So what happens on this is we do exactly the same thing. When we roll a twist, we set up an inductor. The spacing between the two inside conductors set up a capacitor, so that adds an impedance to what we call an impedance to this cable. So this is why when you splice this stuff or you terminate this stuff, you cannot untwist that cable just to make it convenient for you. In fact, the maximum untwist is a 1/4 inch. So you see people run that, and if you untwist it, what you've done is you've changed the characteristics of the cable, which means it won't run as fast. So we'll look at terminating this cable, and we'll also look at splicing the cable. We'll work with this cable a lot because these are pretty standard cables. If you get into networking, then you're going to run into these cables. These are a lot better than Wi-Fi. Wi-Fi is a lot better than it used to be, but it's still very unreliable, and the speeds available on Wi-Fi will never match the speeds that's available on cable. Well, I'm not going to say. I don't see it in the future, but you never can tell. So this would be, we have two categories. We have what we call unshielded twisted pair. We call this UTP cable, which is what you're looking at there. So if this was shielded cable, it would have a metal foil wrapped around it, right? And that would be a true shield. Remember, true shields, you only ground on one side. Y'all understand why? Yes or no? If you ground it on both sides, it's going to be totally impossible for those two sides to be at exactly the same ground potential, which means now you turn a shield into a conductor, which is what they do on coaxial cable. It still has a pretty good function as far as keeping noise in and keeping noise out, but a true shield is only grounded on one side. This is what we have. We have UTP, which is ungrounded. We have what we call 4-pair cable, which there's actually 8 conductors inside there, but they're twisted together. They have a stripe and a solid. So they're twisted together. So we have what? Orange, white, orange, green, white, blue. Orange, white, orange, green, white, green, brown, white, brown. The other color slipped me. Blue, white, blue. A UTP cable. This says screen, so I think this is screen shielded pair. I don't see. This is what would be. This is labeled wrong. This is what would be called STP cable, which is what we call shielded twisted pair. The only place you're going to use STP cable at, it costs a lot more money, is if you're going to run it in an extremely noisy environment. I mean, it's going to be extremely noisy. Most of our connectors have the ability to deal with STP cable, but I've never ran that myself. But I've run a lot of UTP cable. That's before we had a networking department here at the college. So we networked the camp. We did our own network. We networked in fact, the MET department actually had our own network for a real long time. We started out using coax, and then we moved over to UTP. And this has become very popular. So right now, we don't have any phone jacks in our office anymore. So we used to have switch boxes and punch down blocks, and we'll look at some of those. We had rooms that had where they set up and ran the wires for all the telephones on campus. We went to something called Voice over IP. Have you heard of that? So what we do is we actually send our phone over these network cables. So our phones actually go through the network. So we connect our computer and the phone to the same jacks, which is pretty neat. In fact, we connect our phone to the network jack, and then we connect our computer to the phone, because it uses some of the cables to power up the phone. So we're sitting down here basically at the different frequencies. So UTP is for voice frequencies. Which voice frequencies are considered to be, I think, between 30 and 3,000 kilohertz. You can run it how far? We could run it 180 meters. You don't know how to convert from meters to feet, right? pretty close to what? Everybody know the conversion factor? 3.3. But when we get into running at the higher speeds, so originally we ran Cat 3 cable, which we ran at 10 megahertz, and since it's rated at 16, it was we ran it at 100 meters, which is we could run it up to 330 feet without going through something like a hub or a repeater or something like that. Then Cat 4 cable was we ran it at 10 megahertz. And then Cat 5 cable, we run that at up to 100 megahertz, and we still use 100 meters, by the way, even though this chart says it's rated at 90. STP, which is shielded twisted pair, can go up to 300 megahertz at 90 meters. And then we're going to get into fiber later on, 62.5/125 cladding. We'll look at that, all what that means. Its frequency is rated up in the gigahertz, and how far can it go? 2,000 meters. You know, that's pretty close to a mile. And then single mode fiber, and we'll learn these, can go up to 3,000 meters without going through a repeater or some type of amplification to send it on. Later on, we'll get into fiber, and we'll understand what this garbage out here means. Well, fiber there's no way, shape, and form that fiber can handle power. Everybody understand that? Fiber can, it sends information using light, and we can't power with light, right? The jacket rating, we have plenum rated cable, so if you see CPM rating on the jacket, this is for plenum. So y'all know what the plenum is now. What's the plenum? Actually, it was actually the space between the ceiling and the suspended ceiling that was used for air conditioning, what it is. But over time, it's became known as the space between a suspended ceiling and the actual true ceiling. So everything up in there would be considered to be plenum. We don't just run regular cables up. We're not supposed to run regular cables up in the plenum. A lot of cables don't like a lot of heat, and a lot of cables, when you catch them on fire, they put out toxic fumes that will kill you dead. Okay, so a plenum rated cable should be non-toxic, and then it also has a pretty good fire resistant rating on it too. There's almost nothing that's fireproof, right? You understand that? I mean, I can take steel, and if I put it in a hot enough fire, what's it gonna do? It's gonna melt. So we do have what we call fire retardant. It's just like they don't use waterproof much anymore. They used to say waterproof, but now they don't use the term waterproof anymore. They say water resistant, or they say waterproof up to so many meters. Because if you get something deep enough, it's hard to keep things waterproof if you have enough pressure. So plenum rated cables, jackets are designed to run where? You can use them anywhere, but then they're actually designed to run where? Up in the plenum of the ceiling. And we run a lot of stuff up there. It's so dang convenient. I mean, we could drop these things down, and you'd see network cables up there. You'd see coax. I don't know if we ever run coax over here or not. I don't remember. I know I didn't. But you might see coax cable up there. You'll see the old telephone cables up there, because when we went to voice over IP, they didn't go up there and pull all those cables out. They're still up there running in the thing. Very, very convenient. They have special tools to run cable through there. They have fishing rods, so you can put a weight on that. So you can go down on one end on a ladder and open up the end over here and shoot that fishing rod down there and try to ring that hole. It reminds me of my neighbor. He had tires out in his backyard. He was an avid fisherman, and that's what he would do out there. He'd have those tires in the yard, and he'd be out there trying to aim and ring those holes with his fishing pole. So they produce less smoke than traditional polycarbonate, and they smoke and fumes less toxic, right? Riser cables. The problem is that a lot of times we have to run cables up a wall. Now the problem is that when you start running cables up the wall, then now you're concerned not only with pulling the cable and getting it up there, but you're also concerned with the weight of the cable itself, right? You understand? We have cables literally running floors. So riser rated cables defined for uses in vertical tray applications such as cable runs between floors through cable risers and elevator shafts. So what happens is that these guys have got really good strength members inside that cable to do what? To support the cable when it runs up the wall or runs between floors. So we call those what? Riser cables. So odds are if you see an R in the code on the cable jacket, it indicates that that jacket is rated to be what? To be run vertically. CM, these jacket ratings, CM, CMX, CMG, these are what? Yeah, so these are self-extinguishing. These are for use between building floors, air cleaning spaces. Often these cables are used for workstation cables. By the way, we put a thing up there on the inside that handout section in the reference section that gives you what we call a cross-reference. Y'all know what a cross-reference is? A cross-reference means it might specify this, but you can use another one because it either meets or exceeds the specification of the cable. We used to have a company, you can't find them anymore, we call them ECGs. And ECG made transistors and solid-state devices that either met or exceeded the characteristics of the solid-state device you was trying to handle. And they were readily available. They had Mayer Electric up in Birmingham, so that's what they sold, ECG. And that way they didn't have to carry all these 2N2202s and all this other kind of garbage, all these different solid-state devices. They just handled a big line of ECGs. And then you had this book that you would do, and you'd look up the part number you wanted to buy, and then you'd see which ECG replacement that would do that. And so it really, really helped as far as people carrying all those solid state devices, so they didn't have to carry anything. They could just carry one version. Well, that's what cross-reference is. So I might specify like a CMX cable, and then I say, well, I can't get these or I can't find it, and you can look it up in that chart, and it would tell you what other ratings on those jackets that you could use. And that's up there. By the way, I found that the other day and put it up on the site. In fact, all this was defined from where? Yeah, so these are cable ratings. So if you look on the cable and you see this is going to be on the jacket, right? So if you say CMX, anything that's got the C in there, it probably meant CMR, CMX. These are all going to be what? Communication cables. These are going to be signal and power cables. These are going to be what? These are going to be for cables that we use for fire alarms. These are going to be for what? TV, radio antennas. These are going to be for optical fiber cables. These are the designators for what? I don't know, I have to look that one up. These are for cable trays. And of course, these are for network cables, communication cables. And so you're going to have to be careful of that. So if you're replacing a cable, if a cable gets cut or broke or something like that, what they do is they print this information on the jacket out there somewhere. And they do it every foot or so. So what you need to do is do what? You need to find that information on the cable, and you need to do what? You need to replace it with the same jacket grading that was originally put in there, or one that's better. So I think that cross-reference is let me go back to Blackboard if I'm still logged in. Let's see if, I don't think that's it. Circular Mills ampacity. I don't think it's this either. I think this is probably labeled wrong. No. See, we're through that one. through this one, through this one. This is a pretty one that I found. These are acronyms and abbreviations that's used inside the NEC book. So when you start looking at those color things, let's look at, I dropped our NEC chart. Let's see if we can figure out what some of these installations are. So T is what? Did I say T was? Y'all remember? T is thermoplastic. And then if it don't have anything out there, like TW. So TW tells us that it's capable of being used in moist environments, and it's rated at 60 degrees centigrade. If it's got TH, then that's thermoplastic cable rated at 75 degrees centigrade. If it's got THH, then that's thermoplastic rated at 90 degrees centigrade. If it's got the W, that means it's capable of being used what? In wet environments. Okay. So if you look at this, notice these guys here, this is what we're using in our house, 60 degrees centigrade, which would be almost 100, be over 110 degrees Fahrenheit. Then we got RH. RH is an underground cable, so we can run these underground. And then we have TH. These are all thermoplastic. W means it's rated for what? Moist environment. We'd have to look up the FEPs. I'd have to go look these up. But what I've done in THH, so this is THHW, THW2. I used to know what the 2 means. We'll have to go and look at that and see does that explain that. And this come right out of the National Electrical Code book, by the way. And you can look a lot of things up. Code books are not cheap, but you can look a lot of stuff up that's in the book. You can look it up on the internet. You could set up an account on the National Fire Protection Association website, and you could go through the code book, but it was set up so you couldn't download it. So all you could do was go and reference it. Now notice they give it. This was something they added too. They originally the table was set up for just copper. Now they set it up for what? Aluminum, which is pretty neat. And notice if you look at this, the rule of thumb for aluminum is you use 1 gauge higher, 1 gauge higher, which would be which would be 1 size higher. We still, and it's kind of confusing because we say we want to go to a bigger gauge wire. We're talking about the size of the wire. We're not talking about the wire gauge number, right? You understand? So I say a bigger gauge wire, it means a bigger wire, but the actual wire number would be smaller. Rule of thumb is that if we wanted to run aluminum, and I wanted to run it on a 15 amp circuit instead of using a 14 gauge wire, I would use a what? A 12 gauge. So rule of thumb is to go down 1 gauge to run aluminum. Well, be careful with aluminum. What problems does aluminum have? It has a real high coefficient of expansion and contraction. So that means with temperature it changes a lot. So you really have to crimp these things down, because over time, if you run it in a wide temperature change, they're going to work themselves loose, right? Another problem we have is the oxidation rate for aluminum is extremely fast. Aluminum oxide, aluminum rust is an insulator. So what you have to do is if you're going to use aluminum, you have to buy that, they call it paste. But what it is, it's an antioxidant that you wrap around the aluminum, and show you where somebody spliced aluminum with copper, and they put those two things together. Not good. And you can buy aluminum outlets too. It's got aluminum, and they don't use copper. And you know, that's what my son does. He's got aluminum in his house. His house uses aluminum. For a while they did that, until a bunch of houses started burning down because the electricians didn't do what? They'd go out and they'd buy regular the copper-based plugs are a lot cheaper than aluminum-based plugs, because they make more of them. They're mass-produced. Aluminum is not mass-produced. So they would go out there and they're trying to make money, and they would mix aluminum. They would mix copper plugs with aluminum wire, and they didn't put what in there. Put that paste, yeah. They burn up a lot of houses. So, you know, electricians, you take a lot for granted. It seems like it's a simple trade, but just like cable splicing and insulation, it's not a simple trade, because, you know, there's so much you have to know about those cables that you're pulling. Luckily, they do houses. The cabling is the same, just about the same in every one of them. Communication cables, riser. So CMP is a plenum. CMR would be what? Riser. CM would be the commercial grade. Fiber optic cable, which we're going to get into in the second 4 weeks of the course. These would be the designators. Now, this is not the conductor. This is the cable, right? So this is information is going to be printed on the what? On the jacket. If it's an insulator, what they're going to print on there is they print the temperature that it's rated at, and they print the voltage that it's designed to hold in. That's required on the insulator. If it's a combination, then they put a lot of information on an insulator that also serves as a jacket. And these are just different types, STP, UTP. Y'all understand the difference between those two now. So UTP stands for what? Yeah, extended twisted pair, and STP would be what? Shielded twisted pair. This is the characteristics impedance of the cable. This is not the resistance. And there's quite a bit of difference. Impedance, have we talked to you about that? We did talk a little bit about X of L and X of C, right? So when we start adding capacitors and inductors to circuits, we pick up what we refer to as impedance. Impedance cannot be measured with an ohm meter. Y'all understand that? Because it is an AC characteristic. So if I was to take a conductor, UTP conductor, and I was to put an ohm meter across it, it's going to measure infinity if they're not connected together. If I come up here and put some of these frequencies on here, then this guy right here would represent, at its rated frequency, it would represent what? 150 ohms. This would be 150 ohms. This would be 100 ohms. This would be 150 ohms. This would be 150 ohms. That is a characteristic impedance between those wires. Not in the wires, between the wires, right? So RG58 is 75 ohm cable, and RG59 is 50 ohm cable. So you can't mix RG58 with RG59 because their watts don't match. Their impedances don't match. And we got a whole lecture, by the way, on impedance matching. Start talking a little bit more about communication cables. And then fiber optics, we'll look at this later. So that's this chapter. So I'll put the review up there for today. Well, we got to talk about some more stuff before we do our next lab. Let's see what our next lab is.